Hey chemistry students, today we're going to take a look at a couple of interesting issues that come up with determining products of a reaction. So when we look at the different reaction types, it turns out that not every reaction can be assumed to just always happen. Some reactions don't happen. And it's particularly an issue when you're talking about single replacement and double replacement reactions. So here I have an example of a single replacement reaction. We have potassium and aluminum chloride. The question really becomes, is potassium strong enough to kick aluminum out of the bond with chlorine, and potassium to bond with chlorine and have aluminum be on its own? And that's a good question. How do we figure that out? And also in this case of double replacement, we've got sodium chloride and calcium nitrate. If you dissolve them in water, are they going to just all the ions stay separate and dissolved in water? Or are they going to bond together and make a precipitate the way double replacement reactions sometimes do? And in some cases, we're going to write out our reaction and our product would be NR, no reaction. Now, for general chemistry, we're going to assume that every reaction that we write occurs. We're not going to worry about doing this. But if you were to take honors chemistry, and certainly if you take chemistry in college, you'll need to know this. So I kind of wanted you to see it before we take our test, just so you're familiar with the concept. You might possibly see an extra credit question or two with this kind of stuff on it. Okay, so we're going over some special cases of chemical reactions where the reaction might actually not occur. So let's go through each of the types of reactions and discuss how you know what the products will be and whether or not the reaction will occur. So we can predict if they're going to happen or not if we use some extra information. So the 6 types of reactions again are these. You know all of these by now for sure. So in a synthesis reaction, to review, 2 reactants, typically 2 elements, bond to form one product. And of course, you have to balance the charges for that one product. And to predict products, again, you got to look at the charge on the periodic table. I'm sure that the vast majority of you are well aware of this at this point, but I'm going to run through it just in case I catch somebody who didn't know. These elements have a +1 charge. These elements are +2. These elements are +3. Carbon's family here is +4 or -4, depending on what the other element is that it's bonded with. It'll only bond with something of an opposite charge. Nitrogen's family is -3. Oxygen is -2. Fluorine is -1. So for synthesis, again, you've got to balance the charges. For decomposition, it's basically synthesis in reverse. One reactant is broken down into its components. And typically, you're going to see a 2-element compound broken down into its 2 elements. And as long as you write the 2 elements by themselves, you're fine as long as you watch for the diatomic elements. Those are the ones that end in gen or ene, and you'll put a subscript 2 on any of those. Combustion reactions are hydrocarbons reacting with oxygen to produce carbon dioxide and water. And actually, that's kind of a narrow definition. There are other things that we still call combustion that are kind of similar. We're not going to get into that this year, but that's okay. So for our purposes, any hydrocarbon reacting with water will make CO2 and water. Or, sorry, reacting with oxygen will make CO2 and water. And we assume that those reactions will always occur. Now, I should mention, it often takes some addition of energy to get the reaction started, but this is an exothermic reaction, and as long as you get that reaction started, it'll react. So for example, if you were burning a piece of paper, which would be made of hydrocarbons, it just doesn't spontaneously react with the oxygen in the atmosphere and make CO2 and water and fire, which is good. Paper spontaneously burning would be a problem for us. But if you give it enough energy by lighting a match under it, for example, it will start reacting, and then you don't have to keep holding the match there. It just goes on its own. So that reaction is always going to be assumed we always assume that it's going to happen, but we have to keep in mind sometimes you have to add energy to get it to happen. The same is true for synthesis and decomposition reactions. We can get them to happen, but sometimes you have to have energy added to it to get the reaction started. Acid-base reactions, we're always going to assume that they will react. when you mix an acid with a base, it neutralizes. So an acid, of course, is something that starts with an H, and a base ends with OH. And I might swap those two around. Sometimes you write the base first and then the acid. It really doesn't matter how you write it. So you'll see probably both ways on the upcoming test. But when the acid and the base react, the H from the acid bonds with the OH from the base to make water. Always. Always water is one of the two products of an acid-base reaction. And then the other two elements are going to get together and bond according to the rules for balancing their charges. So you need to figure out the charge on them to figure out how they're going to bond together. And this is a special case of a double replacement reaction. In a single replacement reaction, here's where things get a bit tricky. So an element and a compound react in such a way that one of the elements in the compound gets replaced. One of the ways that I show this in class, and if you're in my online class, you haven't gotten to see this because we're not together to act this out. And it's kind of hard to act out with COVID anyway, because you got to touch other students and stuff. But basically what I'll have students do is we pretend we're at the chemistry high school prom, and we have a bunch of, some couples over here and some single people over here that represent compounds and atoms. And so I'll have one single element walk in holding a sign that says maybe +1, and they'll be sodium, and we'll call them letter A here. And they'll walk into the front of the room, and then I'll have okay, so I got cut off there. So I've got a sodium atom who walks in, a sodium ion who walks in, and another couple who comes in, and one of them is holding a +1 and one of them is holding a -1, and they're attracted to each other because they have opposite charge. So they go to the front of the room, and when we're first acting it out, we say, okay, we're going to assume this reaction will happen. So the single +1 who was in the room first will kick out the +1 that was in the compound, and it'll bond with the -1. And then the +1 that was in the compound is by itself now. That's how a single replacement reaction works, but it actually only happens if the single atom is stronger than the one that's in the bond. So if you picture, here's a couple, here's a single atom. This atom says, okay, I'm +1 charge, you're +1 charge, I want to bond with your -1, and they kick the +1 out and bond with the -1. Well, they got to be strong enough to get this +1 to go away so they can bond. Does that kind of make sense? So the way that we know how an element's strength compares to the strength of other elements is called an activity series. So how do we know who is strongest? We use the activity series. An activity series is a list of elements. Let me get this out of the way. And the elements at the top of the list are strongest. So this is ranked in order. So this isn't all of the elements, but these are some elements that will typically be in reactions. So potassium is stronger than sodium, sodium is stronger than lithium, and so on and so forth. So what that means is anybody higher up on the list is going to be able to kick out of a bond anyone lower on the list. So let's do an example here. We've got K plus Li2O. And if you look at the charges on your periodic table, you'd find that K would be a +1 ion, and lithium is going to be +1 ion also, and oxygen is a -2 ion. So it's possible that potassium and oxygen would like to bond together because it's a +1 and a -2. So we're going to check and see, is potassium strong enough to kick out lithium in this bond with oxygen? Well, potassium's the very top of the list, and here's lithium down here. Lithium is weaker than potassium. So potassium will kick out lithium. And so the product will be potassium oxide plus Li by itself. And it's not going to have a subscript 2 because it's not diatomic. It can be alone. So then you have to figure out the charges. K is +1, O is -2, so that'll be K2O. So the product on this first one would be K2O plus Li, or Li plus K2O. On the second one, we've got calcium and lithium oxide again. So let's see, is calcium stronger than lithium? And here's calcium. It is below lithium. So calcium will not be able to kick lithium out. That means this reaction is not going to happen. So we would put NR, no reaction, not going to happen. And I don't know why it keeps auto-correcting my arrows. See, that's a normal arrow here. And here it's got an A with a hat. Anyway, that's very strange. It likes the arrows here, but not the other one. So in this one, we've got iron 3 chloride and lead. So let's see if lead is stronger than iron. And lead is down here and iron is here. So lead is not stronger than iron. Iron is already in the bond, so it's going to stay in the bond. So we would write NR, no reaction. Okay. Double replacement has a similar set of weird rules. It's different, it's just similar in that it's got weird rules here. So in double replacement, and this is a fun one to act out with my students in class, we have two couples that arrive at prom, a +1, a -1, a +1, and a -1. And they react in such a way that this +1 bonds with this -1, and this +1 bonds with this -1, and so we have two new couples. You have to pay attention to charges, and remember we said we call these precipitate reactions, which means you get a solid in the products. One of the products is going to form, double replacement only happens when one of the products forms a precipitate. So we would first predict the potential products and then check to see if they're both soluble. If they're both going to dissolve in that water solution, then no reaction is going to occur. And if they're not both soluble, oops, let me get rid of my face here. No, can't. Okay, so anyway, we're going to check to see whether or not they're both soluble. If they are both soluble, then no reaction will occur because you had two ions that were bonded together that you mixed in a solution and they separated apart. And then when you mix those together, nobody really bonded and they just kind of stayed separate. So if one of them is not soluble, that means it becomes a solid when you mix the two together, then we say, yes, a reaction did happen and the solid precipitate is the product of the reaction. So the solubility rules look something like this. They can be written a bunch of different ways. Sometimes you'll see it as a table. You would not need to memorize this unless maybe once you get into college, you would have to memorize it. No, honors chemistry does not memorize it, but I think maybe AP Chem does have to memorize some of the rules. So the rules tell you when you're going to see a solid product. So for example, rule number 1 says that salts, which just means ionic compounds, compounds containing group 1 elements are soluble. So group 1 is column 1 on the periodic table. So any of those elements as part of a compound are going to be soluble in water. And there are some rare exceptions to the rule. It's not something you'd need to know. Also, salts containing the ammonium ion are also soluble. And salts containing nitrate ions are generally soluble. Salts containing chlorine, bromine, and iodine are soluble, and so on and so forth. And so each time you want to do a double replacement reaction, you would have to look at this list to see whether you get a solid product or not. If you don't, you just write NR, no reaction. So if both products are soluble, you write NR. If one product is insoluble, then the reaction occurs. Let me give you a couple of examples. So here we have sodium chloride and calcium bromide, and they're going to react in such a way that sodium bonds, it's going to be the positive one, bonds with the negative one in the other compound. So sodium bromide is one of your potential compounds. And then calcium chloride is the other one. So we have to go back and look on our activity series. Sodium bromide, well, sodium is a group 1 element. All of these are soluble, so that's going to be soluble. So we would write sodium bromide, parentheses AQ, to say dissolved in water. And then calcium's not in this list early on, but it does say salts containing bromine are generally soluble. So that's going to be soluble too. So that means, in this case, we'd say calcium chloride is soluble, sodium bromide is soluble, therefore, no reaction. So here's another example, silver nitrate and potassium iodide. Silver nitrate, whoops, and we don't even really have to write out the formulas here to do the problem. So silver nitrate would become the silver would bond with the iodide. So silver iodide and potassium nitrate are the two that we need to check. Is silver iodide or potassium nitrate soluble? So we come back to our solubility rules. Here they are, silver iodide. So it says here, salts containing chlorine, bromine, and iodine are soluble except for with silver. So with silver, that's insoluble, and so that one is going to actually happen. A reaction is going to actually occur. So we're going to say, yes, this reaction occurs, and silver iodide is one of the products. And the other product we had was sodium, nope, wrong one. Potassium nitrate. And if you recall, the list said that potassium, being a group 1 element, almost everything is soluble, and also nitrate compounds are almost always soluble too. So that's going to be soluble. So our product, so we say the possible products are silver iodide, that's insoluble, and potassium nitrate, that is soluble. And so silver iodide, that's our only product. And then we could write the separate ions that would be left in solution. Okay, so here we go. We're going to go ahead and work out these two problems. So first thing you want to do is to write out the charges of each of the ions that you're going to work with. Potassium is a group 1 element, so +1. Aluminum is +3. And chlorine is -1. Now you can see, because opposites attract, that potassium might bond with chlorine. And if it did, we would get KCl, and aluminum would be kicked out by itself, so Al. So the question is potassium strong enough to kick out aluminum? And when you look at your activity series, you'll find potassium at the very, very top, which means it's strong enough to kick out anybody in any bond. Any metal, it'll kick out. So this reaction does happen, and that's the reaction you're going to get. For the next one, it's a double replacement. Again, you need to look at the ions. So we've got sodium with its +1 charge, chlorine with its -1, calcium is +2, and on your polyatomic ion sheet, you can look up nitrate. Nitrate is NO3 -1. So if this reaction occurs, what will happen is that sodium will bond with nitrate, and we get NaNO3. +1 and -1, we just need one of each. And this substance is going to be AQ. We know that group 1 elements like sodium almost always dissolve in water, and nitrate molecules always dissolve in water too. So that's going to be AQ. I'm running out of space here, so I'm going to squeeze this in. Plus, calcium is going to bond with chlorine. We always write the plus first, the positive ion first. So CaCl2. Ca +2, Cl -1. We need 2 chlorines to balance it. And when we look up calcium chloride on our solubility chart, we also find that chloride compounds are almost always soluble, with some exceptions. Calcium is not one of the exceptions, so this will be aqueous too. As a result, we have 2 aqueous compounds that are not going to form a precipitate. And if a precipitate doesn't happen, we say this is no reaction. So actually, the products of this, there aren't any. So we write NR. Okay, I hope that little bit of background was useful for you, and kind of some good review and a little bit of extra information.